Hi, everyone. Today is our first lecture on a category called simple harmonic motion. There are a couple things that you guys are going to need to know when it comes to simple harmonic motion. And we're talking about what it actually is, what could qualify as simple harmonic motion, so things like pendulums and mass spring systems. We're going to need to know the definition of oscillation, equilibrium position, and also what is a restoring force. So simple harmonic motion is a category of motion where we see a repeating pattern over and over. And we pretty classically see this in three different systems, one of which you may have seen before, where we have a mass at the end of a string and it swings back and forth. You guys know what I'm talking about here. We're talking about some kind of a pendulum. Okay, so simple harmonic motion is just a repeating pattern. And when we see a pendulum swing back and forth and back and forth, we would say that that is a repeating pattern. We also may see something called a mass spring system. So that'll be kind of like our second category. And we can have a horizontal orientation of a mass spring system. And what it consists of is a spring attached to some kind of immovable surface or object. And at the other end of the spring is some kind of mass, and that mass is allowed to move. So that mass may end up going to the right, it may end up going to the left, but essentially this mass is allowed to kind of like bounce between those two locations. And we see mass spring systems not only horizontally, but we can see them oriented vertically as well. So we may have some kind of spring attached to a mass. And again, that mass could move downward and then bounce back upward. And we would see it go back and forth and back and forth and back and forth and back and forth between those two locations. So that's what we mean when we are saying that there are three classic examples of simple harmonic motion. We would be talking about the pendulum, the horizontal mass spring system, and then the vertical mass spring system. Now, what are some qualities that we look for in simple harmonic motion systems? We really have two major qualities. The first of which is that the system undergoes what is called oscillation. An oscillation is a fantastic vocabulary word that we should define right here. So oscillation is the regular variation in position around a central point. Okay, so if we go back and we look at our quick little drawings that we had here, we see that in all three of these situations. So for a pendulum, right, the central point is the center of the pendulum. So my pendulum is, oh wait, no, more like my central point is not straight. Let's try that again. Yeah, so if we look at this, we would see that our pendulum is regularly going to the left-hand side of our central point and to the right-hand side of our central point. If we look at the horizontal mass spring system, right, this would be our central point. And we are regularly moving to the right of that central point and then coming back, moving to the left of that central point. And then yet again, we see that for the vertical mass spring system as well. We go below our central point and then we come back and go above our central point. And that central point has a specific name. We would call this the equilibrium position. Now, how do we know where the equilibrium position is? Well, the equilibrium position is really the location where if we take our mass, so whether that be the pendulum bob or the mass that's attached to the end of the spring, if we specifically place that mass at the equilibrium position at rest, we would not see any motion at all. So if our mass attached to the end of the spring is specifically located right here, where there is no stretch in the spring at all on this horizontal mass spring system, and then we let go, the mass will just stay there. It is at equilibrium. It is abiding by Newton's first law right then. All right. Let's talk about the second quality of simple harmonic motion. And we want to detail that simple harmonic motion is being caused by two things. So there are two things that we must satisfy in order to cause that simple harmonic motion. Quality number one is that we must have some kind of displacement from our equilibrium position. Otherwise, just like what we just said a second ago, if we place our mass at that equilibrium position at rest, leave it alone, it's not going to move at all. We will not see that repeating pattern of oscillation back and forth. So we have to have some kind of displacement. We have to take this pendulum, we have to pull it away from its equilibrium position and then allow it to go. And that's what causes that simple harmonic motion of the pendulum. We need to take our horizontal mass spring system, we need to pull it, or conversely, we could push it if we wanted to. But most of the time we pull it and we stretch out the spring, we move away from the equilibrium position, and then that causes our mass spring system to start moving in simple harmonic motion. So that displacement is required. The second thing that we need to have is we need to have what is called a restoring force. And restoring force is really just a force that you would see on your force diagram that is towards the equilibrium position. So it's going to be different whether we're looking at a pendulum or we're looking at a horizontal mass spring or we're looking at a vertical mass spring system. Okay, so let's define restoring force. That is the force towards the equilibrium position. And there's a second thing that we should know about this restoring force. It's that it is proportional to the displacement from the position. Okay, and again, excuse me, I'm going to talk about this horizontal mass spring system to kind of explain this a little bit more clearly, this idea of the restoring force. When we bring our mass, perhaps we bring it to the right of equilibrium, and we stretch the spring as a result. That stretch of the spring is going to cause a spring force that is going to want to pull to the left. And so that's what causes this box to then move to the left once it is released. And it sets it into that simple harmonic motion where we suddenly are bouncing back and forth to the right and to the left of equilibrium. Now we know from Hooke's law that spring force is proportional to the displacement, okay? It's proportional to this x. So more that we pull our mass and the more that we end up stretching our spring, the greater our spring force ends up being. And since the spring force is the restoring force in this situation, right? That explains what we mean when we say that it is proportional to the displacement from the position. Our force, our restoring force is strongest when we are at the extremes of our oscillation, and it is least, and usually in fact zero, when we are at the equilibrium position.